Today we are going to see what is the need to study this compiler. Can anyone answer me? Actually, this compiler is the base for all programming languages. First of all, here we are having, it's a microsome of all the computer science subjects. So we are going to study some of the greedy algorithms, learning algorithms, all the learning algorithms, how we are making the system to learn about how to compile the program, right? So we some artificial intelligence concepts there. And here we are having some dynamic programming based on the inputs we have to change the codes in the, right? And also when you are taking this phases of compiler, in each phase, first of all, you have to get the input from the user. So then you need a scanning process, and you have to check whether the input what you have given is correct. And then you have to parse your sentences. And then you have to go for semantic analysis and all, right? Then only you can go for code generation. So you need to know about automatas, and also theory of computation is required there. Hope you have already studied all this in DFA, NFA and all in theory of computation. So you need to know about automatas, and also theory of computation is required there. Hope you have already studied all this in DFA, NFA and all in theory of computation. And also we have to know about the allocation, memory allocations. When you are generating machine code, you should be very clear about architecture, machine architectures, and what are the different types of register modes available and all. Okay, so you have to know about some of the system softwares, as well as when you are assigning these instructions. Only when you know about the architecture very well, it will be easy for you, right? So all these things come together as a compiler. Can you hear me, ma? Students?
Yes, ma'am. Yes, ma'am.
Yes. Okay. So, and the main problem in compiler design is when you are generating machine code, the architectures are changing, constantly changing. Every time we are getting new architectures and all. So new features are coming. Whenever a new feature is coming, it has to be adapted. Whatever we have generated as a compiler, that should be adapted now for the new architecture. So, and based on the architectures, if we have to redefine our codes, means that's a problem there. And some of the old solutions, we need to do some re-engineering processing, right? So these are some of the problems. I mean, as we are facing it when we are having constantly new machines are coming out, right? And we have to these are all very basic concepts, right? Whatever we are going to study in this compiler design, these are all very old concepts. Everything is already available. What we are expecting is we have to design a compiler such that it has to adapt with all type of architectures, right? So it's in your hand. If you are studying all the basic concepts, it may be you may come up with one new compiler, right? So what are the qualities we require to be to have or to design a compiler, right? First of all, when the programmer is giving an input, you have to generate a correct equivalent machine code, right? So your compiler should be designed in such a way it has to get all the information as such from the language in a form of a high-level language program, and it has to generate the code which is equivalent to that high programming language, right? And when you are generating this machine language code, you have to check optimization process. You are having optimization process and all, which will help you to find the code which will run faster. So that outputs, and after generating your object code, when you execute that output should be generated in a fast manner, right? So output should be very fast, right? And the compiler, when you are doing this compilation, that means you're converting the high-level programming language into object code. That process itself should be faster. So your compiler should be it itself is a program. Compiler itself is a program. That program should be designed in such a way, in a simple form, as well as it has to use some of the instructions which will be executed by faster, right? Normally, based on your program size, compile time will be varied, right? So you have to generate a code based on the consideration of number of instructions available in your program. Okay, and in case if you need some separate compilations for macros or some things, means you have to support that. Your compiler design should adopt to that, right? And when you're finding some errors in your words whatever you have used in your program, or if you're creating some sentences in your program, no, I'm just telling in a form of a literal meaning first of all, because after getting into that phases you will come to know what is syntax analysis and all, right? So whenever you are writing a sentence in a program, instructions in a program, like it may be an assignment statements, or it may be some of the decision structures, or it may be looping structures, right? So there may be chances to have some errors when you can write, you may write a program with some errors. So your compiler should be designed in such a way it has to find all the errors, but whatever you have done there, right? It should not miss out not even a single error, right? Error sentences. And next one is, in case if you want to debug the programs, your compiler should work with that debug program. Okay, and one more thing is, not only it is generating code, it has to keep in track of how the data is flowing, right? For example, when you're declaring some variables from the first line to the end of the line, wherever you're using that variables, you have to keep in track. Whenever you are changing some variable values, that should be reflected in all the sentences wherever you have used. So the flow of data or the flow of variables wherever in all the sentences throughout the program should be uh, recorded using your compiler program. Okay, and sometimes in nowadays you are getting many programming languages which is supporting or execution of some of the functions which is available in other languages, right? So if you are taking MATLAB, it is supporting some C routines, right? So your compiler is in one form and you're for designed for one language, but it has to extend its features so that it has to support execution, or it has to accept the executed code of other languages. So it should accept that cross language calls. And whenever you are doing optimization, that should be a consistent as well as predictable one. So if you are generating a code and when you are doing optimization, this should be your you should have, when you're doing by own, you should that compiler program should be in such a way, it should be in a form which is easily predictable, right? Okay, so let's see what are the different stages we have come across from the starting initialization of these programs. In 1950s, Fortran. Fortran is the first programming language, which Fortran 1, which is for this, we have designed this compiler. And actually, in 1952, there is one more compiler with linker and loader concepts is used for A0, A0 programming languages. And 1957, a complete compiler. Actually, initially they have started that design of compiler as a combination or ensembling of all the different phases of compiler. They are, everybody is generating one part of the program, right? They are not taking the compiler as a whole program. Every phase is done by as a separate processor or a separate program, and they are combined together, right? But the first complete compiler for Fortran was designed by John Backus and team in 1957. And after that, in 1960, for COBOL programming language, they have started created one compiler. And in addition to that, Alga, Lisp, Simula, and these are the programmings for which the compiler has been designed. And self-hosting compiler for Lisp is generated in 1962. Okay, and in 1970s we have come across some of the object-oriented programming languages. So see, we have started with structured programming languages, and then proceed in the structured with procedure-oriented programming languages, and then object-oriented programming languages. So based on the types of programming language, the compiler versions are also changing. And in 1990s we have started with Java. So Java programming language needs to be run in all the machines and it should have the feature of portability. So just-in-time compilers are being generated. And the next one is phased compilation. And here we are having both, we have to keep track of both compile time as well as runtime. Okay. So we will discuss these part phased compilation later when we discuss about the phases of compiler, right? So actually it refers that the compilation is not taken as a single unit. It's been defined as what are the phases we are having in front end, what are the phases we are having in back end. That phases has been generated, right? So next one is so this is the overall view of a compiler. So yeah, a compiler is nothing but it's a translator. It's getting on source code, which is in high level programming language, and that will be converted into machine code in the time of compiling. And when you in the time of generating machine code, if you find some errors, if the compiler is there finding some errors, that error messages will be generated. Okay, so this is the overall abstract view of compiler. And as I told you, the compiler is not taken as a single program which is combining all the things together. Have you studied networks, ma? Have you studied networks, students?
Yes, ma'am, last semester.
Yeah. You have studied architectures and all, no? Why do we have different levels of architecture in ISO, OSI model and all? You are having application layer, presentation layer, network layer and all we are having, no? Why? So every layer is having its own process. It has to do some job, and it is not depending, or you can say the output of one layer is given to the other layer, right? So as if you just imagine all the things, all the process to be done by a single program, what are the difficulties you will face, right? Everybody should know about all the programs when you are defining one network, right? So in the same way, when you are defining this compiler, instead of taking the whole thing as a single program, they are dividing it into phases, and the series of phases will be generated. The output of one phase will be given as an input for the next phase. Okay, and now we are having 6 or 7 phases, but initially they started with only 2 phases, right? One front end and one back end. Front end part is used for analysis of your program. It will be in a it will get the input high level programming language, and it will analyze it whether it is a correct programming, and then it will give that to a synthesis phase or the back end phase. Here it will do the job of conversion, right? The translation into machine language or the target language. So the traditional 2-pass compiler is like this only: source code, and when you're doing in this front end analysis phase, it will generate intermediate code, right? Intermediate representation. I will tell you what is intermediate representation, and from this intermediate representation, it will convert this intermediate representation code into machine code in using synthesis and a part, that is our back end part. Okay. Actually, what is the need to this IR is, for example, if I am having 4 programming language, right? Let me take Fortran, C++, CLU code, and Smalltalk. These are the 4 different programming language, right? But when I'm using traditional 2-pass compiler, for each programming language, I have to design one front end and one back end. Okay, so in the case, if I want to convert Fortran code into machine language, that is target 1. Let us take target 1. Target 1 is your machine language. Target 2 is an assembly language. Target 3 is some other languages, right? So if I want to do this, let us take the first Fortran code. From this Fortran code, we have to go through this front end, and then we have to generate backend for target 1. Similarly, backend for target 2, backend for target 3. Right? Similarly, when you're taking C++ code, you have to do this process of front end, and then again we have to come for different backends for target 1, 2, 3. Right? So if I'm having 4 programming language, I should have 4 into 3, 12 process to be done. Okay, so to avoid this, actually backend processes just it is generating a machine code, right? So what we are doing is instead of directly giving that output as after synthesis, we are going to generate one intermediate representation, right? So that intermediate representation, what it will do is, actually this program, this structure itself, it will not be like this. for each and every one, we are having three parts, right? Backend part for target 1, backend for target 2, backend for target 3. Like this for each programming language we used to have. But with the help of intermediate representation, the front end part will generate this intermediate representation. And once it is converted to intermediate representation, this intermediate representation is a common format, right? Whatever may be the input programming language. It may be a Fortran programming language or C++ or CLU or Smalltalk, whatever may be. But that intermediate representation will be like your assembly language program. It will be very easy. Intermediate representation is, right? So this intermediate representation will be a common form. Now it is very easy for you to convert that intermediate representation to target 1 based on backend, or you can go for different synthesis for target 2 or synthesis for the target 3. Okay, can you get my point? Actually, when you are taking this, the first one for front end one, we have to write one backend for target 1. Okay, or just imagine if you don't have these two phases, front end and back end, right? So what you have to do is you have to write all these two processes together to create target 1. And similarly, front end as well as back end for target 2, and front end and back end for target 3, right? Three things you have to, three processes you have to do. In each of the processes, we have to complete both front end process as well as back end process, right? But if I create a compiler in two phases with front end and back end, in this front end output, we are going to have intermediate representation. This intermediate representation is common, or it is in a common representation. Whatever may be the input you are giving, the IR will remain same. Okay, so we are going to convert this into M cross N combinations. Like the front end will be converted into IR for the first one as well as for second one, and then you will have single backend, okay, for a single target one, for a single target programming language. So the backend is varying only if you have a different target programming language. Otherwise, there will not be any changes. So that's why we are going for this traditional two-pass compilers.